Hey everybody. So I hope you've been having some fun playing around with ml5js and the idea of the neural network. And I wanted to share something that I thought about this weekend as I was putting this together. A very common thing that you want to be able to do with a robot is know exactly where you are. If you know where the robot is, you can know the robot can drive autonomously from one place to another, similar to what we've done in some of the tasks in our class. One idea that I had, which is related to this question of figuring out where you are, is whether machine learning could help. And so here's what I was thinking. This process of trying to figure out where you are is known as localization. And I was thinking about this scenario, and you can kind of see this situation on the left-hand side of the screen here. The idea is, suppose you have some beacons. And so beacons are just these radio transmitters that are in specific locations. And based on how strong the signal is from these transmitters, you can figure out how far away it is. So thinking about that, I have these dotted lines here on the screen showing just kind of giving an indication of a straight line between where the mouse is and each of these beacons. And so you can see at this point, the location of my mouse, which could be the robot, is much closer to the top left beacon than it is to the bottom right beacon. And you can see that just from the two lines. And so my question was, you can kind of figure out the strength of a signal from a beacon just by usually this is something that is reported by the beacon over the radio. And so my question was, could you use that information in order to figure out where you are on the plane? And so you can see here that as I move around, those distances are different. This is a problem that you may have seen in geometry, where you talk about the locus of points that meet a condition. And so one example of a locus of points that you're often asked to find is the set of points that are the same distance away from 2 points in space. And so we can kind of eyeball that right here by saying this seems to be about the same distance between the two. These are the same distance. This is a little too close to the one in the bottom left, so let's move it over a little bit. And so by this you can sort of figure out that there's a line of points that is equidistant between those two points. And so the reason I bring this up is that with two beacons like this probably is not enough information. If I tell you my distances from the two beacons, if I tell you that the distance is the same, then I know I'm somewhere along this line. Okay, if I tell you that the distance from both is, let's say, I don't know, 10 centimeters, then I'm telling you specifically that I must be at this location, because if the top left line segment is 10 and the bottom line segment is 10, how many different places are there in the plane where that might be true? Well, it could be here. It also might be here. And so with two beacons, that might not be enough information. I've included some code to make it so that I can include different numbers of beacons. So I'll just add on a third beacon here and reload. Oops, I have an error. There we go. Okay. Okay, so 3 beacons now, and you can imagine maybe I get a little more information from that. I also have a 4th beacon in here that I'll add in, and you could imagine we could continue this whole process and add as many beacons as we wanted, as we might want. Now, the reason this is significant, the reason I'm bringing up this idea is that maybe we could train a machine learning algorithm to know, given, let's say that the inputs to our machine learning algorithm are the distances to each of the beacons. And I could say that I know where I am at a bunch of locations here on the plane. And so from a bunch of those locations, I could basically use that as the actual position of my robot as it's moving around between these two things. So what I am creating here is a set of training data, just like in the thing you put together, where my input is a bunch of distances to each of the beacons, and the output is an x, y coordinate to tell me where we are. And so this was my idea, and I know there is math that might help to make this, to do this a different way, but I thought it might be kind of cool to be able to use machine learning as a way to quickly figure out this relationship without having to do all the trigonometry and get out my textbooks and do a whole bunch of linear algebra. So I want to show you how this works. I'm going to turn off those lines. I want you to have that in your head as we're doing this. Let me save that and reload. And so what I can now do is I can click around the plane and just say that wherever I click, I know the coordinates of those points. But I also can calculate my distance from each of those beacons. I do that down here using the distance formula. See that? That's just the straight distance formula from geometry. And so I can do this and kind of click all the way around, give my algorithm a whole bunch of learning data like this. And I don't know how much to really give it, so we can just kind of guess and put this out like this. And then what I can do is hit T, which trains my algorithm. And so if I go to the console, it'll tell me when it's done. I could also turn on that nice little diagnostic window that pops up. Let's go to the console. Let's see what it says. Console. And let's hide that. Okay. And so it is actually telling me from all of that. Looks like it's not quite done training yet. Oh, it is done training. Never mind. And so now, as I click through, you can sort of see just from that training data that I gave it, it's able to do a pretty good job. It's not so good as I get toward the edges, notice that? And that was something I was kind of looking at, trying to understand, like why is it not so good when it gets to the edges? And it's because neural networks are really good at interpolation, that is finding points between two values. They're not so good at extrapolation. In fact, they're terrible at it. And so if you look at this, most of the points that I clicked in here were really close to the edge. And so, they were not really close to the edge. So as I was training this, it does a pretty good job when I'm in the inside of the space, but when I get to the edge, look how far away that is from where I'm clicking. Okay. I want to show you I have a bit more of a systematic way to go through this as well. Let me reload. That is, instead of clicking all through the plane, what I instead might be able to do is just create a bunch of points and use those points to train. So to do that, I can hit the A key, and that just generates points all throughout the plane and also stores the distances to all 4 of those beacons. I can train my algorithm. Actually, let me do that one more time. Turn on the debug so that you can kind of see how this is doing over time. Let's do that one more time. Reload. Okay, so there's A, and let's train. So if I slide this over, sort of see it training over time, and it is sort of settling around 0.6, so it finds the optimal set of all those weights, finding the relationship between the inputs and outputs. It does so pretty quickly. Is it getting any better? Yeah, I guess it is. So it gets a little better over time. Okay, and it looks like it has stopped now, and you can sort of see it gets better around here, and then it really just sort of bounces up and down. So probably this last 100 epochs, I don't really need it to be training. Let's hide this. Okay, and the other thing that I can do now that I have trained this is I can click through and you can sort of see how well it's doing, which is not great. That's a little strange. But I can also do Q, hit Q on the keyboard, which actually generates an array of points. Oh, no, actually, I don't have that enabled right now because I clicked, didn't I? Okay, so let me try this one more time. And I'm going to change the number of epochs of training from 200. I'll change it. I'll leave that where it is. That's fine. But this time I'm going to use the A key, and I'm not going to show the training data. So it'll actually go a lot faster when it's not generating that graph. And then afterwards I can hit Q, which does the same thing. It goes through a series of locations and clicks through, and then shows the locations of those points using the neural network to predict. Okay, so now I've gotten this message that it has finished training. So let me just shrink that down a little bit. And so you can see now the location of each of those points that I initially started with. And in pink or magenta, you can sort of see the locations of those points when they're fed through the neural network. And it does a pretty good job. I mean, I'm impressed with the quality there. It's not so great close to the edges, which is what we saw already. But in the middle, it does a reasonable job, and it's good enough that maybe it's good enough to know that your robot is here as opposed to being over here. I can increase the quality here by using instead, let's say instead of 10 dots going all the way across, I could do 20. Make a bunch of points. Make a bunch of points so you can see a lot more there. Let's train, and we'll wait to get our message down there to say that it has finished training. Okay, so it's finished training. I hit Q, and let's see how good it is. All right, so with more points, it's even more accurate. You can see a lot of these are really, really close to where I clicked beforehand. It is a little bit farther off at the edges, but it does a really good job. So there's one last thing that I want to show you, and that is the idea. So your math teacher would come in and tell you, you don't need 4 of these beacons. You don't need them. You can do this whole thing with 3. And so my question is, you might think, why would we need 4? Well, what if one doesn't work? What if you lose contact with one of them? In the real world, you don't have perfect locations of the beacons. It's rare for everything to work all the time. So let's actually go back to the situation where we only had 3 beacons. And let's try doing the same analysis and see how it does. All right, so with 3 beacons, let's take a look. And so with that missing information, you can kind of see it still does an okay job. I mean, it's kind of impressive. Over here, it's a little bit weird. This click goes here. This click goes here. But in the middle, it still does a pretty good job, even with only 3 of these. So the obvious question now is, what happens when you reduce it down to 2? Let's see. All right, so it's finished training, and let's look and see what each of these clicks turns into when run through the network. So you can see that this is really bad. This does not do a very good job at all. So having 2 beacons certainly is not enough information. So what I look at this as telling me is that if I wanted to do this system, I would need 3 beacons, if not 4 or 5 or 6, in order to do a really good job of this. So this is just an example that I had over the weekend and that I wanted to share with you. This is something that we could theoretically do, maybe with Bluetooth devices. We could make some beacons, get some microbits that are constantly reporting their distance, and maybe use that to do a locator system within the Idea Center. I don't know if this is possible, but I just wanted to throw this out there to show you that some of these things that we're doing, it's really easy to use a machine learning algorithm to explore an idea that you have. And this brings me to the only thing that I'm looking for you today, and that is thinking about what I have had you do already with machine learning. I want you to share some of the ideas that you have on how we might be able to use these concepts to make something practical. So think about it, and I want you to share your ideas, send them in to me, and we'll talk about them next time. Have a great day.